Let's look at another example of differentiating a function graphically. So a classic example of this kind of function is the absolute value of x. This is not a function that we can apply the usual shortcut rules to so easily, but we can get a picture of its derivative very easily, and then we can write down the equation or the formula for that derivative. Okay, so here's a graph of the absolute value of x. Remember that anything that you plug in, any x value you plug in to this function, spits back out something positive. So really it's the picture of x, which would extend down here. We take the negative part and we sort of just bend it up to be positive. So it's a V shape. Okay? And we can actually differentiate this function even though at one point it's not differentiable. And that's the point right here at 0. At 0 there's a problem because it has a corner in it. But we can still get a picture of its derivative and then actually write down a formula for that particular function. Okay? And this same technique will work for any kind of function. So let's do this. First of all, we notice that the absolute value of x, if I've drawn this right, will always have a slope of -1 over here. The slope is clearly negative. But the slope is the same everywhere, right? Because it's sort of linear. And same thing goes for the other side of 0, right? For x equals 0, I should say, the other side of the graph. On this side of the graph, the slope is again linear. It's always the same. As we increase in x, we increase exactly the same amount in y, except it's positive. So in fact, the slope over here is -1. The slope over here is +1. And right here, we just have some weirdness going on. Okay? It's not differentiable at that point precisely because we shift very rapidly from having a negative slope to a positive slope at one particular point. Okay? So let me write that down in more detail. That is that over on this side of the xy plane, we have a slope negative. So the slope is always the same for every single point over here. The slope is in fact -1. Over here, the slope of the tangent line at every single point, of course, every single point in this whole line is really a tangent line, right? So the slope over here on this part of the graph is +1. Okay? Except at 0, there's something weird. It's not differentiable there. But that's okay. We can still draw the picture of its derivative. So let's draw the picture of the derivative of this function in blue. Okay, so I'm going to write this as the derivative of f. It's right over here. And we're going to use the same techniques we've done in the past, which is if the slope is negative, we write it below the x-axis, the horizontal line. And if the slope is positive, we write the picture above. Meaning that, remember, the slope is really over here, the y value, right? So we have that y is equal f prime, but that's equal to the slope of tangent line. Okay? So all of our y values will be exactly the slope of the tangent line. Again, something weird happens here, and we'll see exactly why, in fact, this function is not differentiable at the point 0. You can sort of see it graphically. But let's just go ahead and draw the picture. Again, every single point over here gives me a slope of -1. So that means the derivative for every single point from, not including 0, but everything back over here, the derivative is -1. Okay? So that means if I want to draw this, the derivative, or the y value, is -1. Well, here's y equal -1. Okay? And I'm going to draw the line, an exact horizontal line, because the derivative is always the same. It's just a flat line. It's always -1. Let's say that's -1. Over here, on the other side, the slope is +1. So the y value is always +1. For every single x value, the corresponding derivative is +1. Or the slope is always +1. So let me draw +1. It should be equidistant. Let's go over here. Y is +1. I'm going to draw, again, a horizontal line because, for the same reason, again, the derivative is always +1. The slope is always +1 for every single x value. So it's a constant. The only thing is we have to be a little bit more careful here because at 0, it's really not differentiable, meaning it sort of jumps. It takes on two different values. And we want our derivative to be a function, So we can't have it take on two separate values at the same time. That would violate functionness, right? So what I have to do is just put a little hole in the graph here at that particular point. So to draw this properly, I would have to do something like this. Okay? That is, it's not really differentiable here. We can certainly put a value in there, but we're not going to now. The point is that this is actually the picture of the derivative of this function. Okay? And I can actually draw or write down a formula for this as well. The formula for this is just going to be exactly the definition you can see here. So in fact, the derivative of f is really something like this. It's going to be the y value is plus 1 for all x values that are above 0, and it's negative 1 for all x values that are below 0. Okay? Sometimes we call this the so-called sine function, not to be confused with a trigonometric function. But for now, don't worry about that. Just think about how we define it. We just have to define it in pieces, right? It's kind of weird. It's not really what we are traditionally used to seeing, but it's a perfectly legitimate function. It's a function because it takes on only one output for any given input. Okay, so here's my derivative of the absolute value function. It's not something that we know how to do with shortcuts in the same way as polynomial functions, for example, but if we use the power of graphing, we can get a picture of the derivative and write, in fact, down a perfectly good formula for the derivative of the absolute value function.